Hello, welcome to lecture 9 of the digital logic class, and in this part we are going to discuss decoders and just give an idea here of what we are trying to do is um, basically we have the combinational circuits. Um, we looked in the previous class or lecture at adders, subtractors, um, magnitude comparators. And in this class, we will look at decoders, encoders, and multiplexers. These are basically combinational circuit blocks or units, if you want, and they come under the topic of combinational, combinational, combinational circuits. And combinational circuits, we looked at how we design simple circuits and analyze them. And then we moved to the topic of the um, circuit blocks. And today we are right here at the decoder topic. Okay. All right. So, what's a decoder? What does the decoder do? The decoder is a circuit. Well, that's not what I intended to do. Is a circuit, okay, which has um, is a circuit. This is the decoder, okay, and typically it has in inputs and two to the in outputs. Let's take an example. Assume I have two inputs. Let's just say A and B. Of course, how many inputs I have? Two. How many outputs I should have? 2 to the 2, which is 4. So this is, let's assume it's D0, D1, D2, and D3. And the function of the decoder, okay, so this is a decoder, and we say that this is an n by 2 to the n, so 2 to the n, so in this case it is 2 by 4 decoder. Okay, so how does this work? Well, let's have a truth table here that explains um, the combinations of A and B. So they can be both zeros, 0, 1, 1, 0, 1, 1. And then here you have the outputs, D3, D2, D1, and D0. So basically, we activate, so this is D0 here, we activate the output, which corresponds to the value of this binary number here. So when A and B are zeros, this binary number here is 0. So what do? We activate D0. D1 will be 0, D2 will be 0, D3 will be 0. Now, suppose we have 0, 1. This binary value equals 1. 0, 1, it is equal to 1. So now we activate D1. The rests are 0. And in this case, this is a binary value of 2. And we activate D2. The others are zeros. And finally, here 1 and 1, which corresponds to the binary value, corresponds to the, yes, binary value of 3. Okay, so we activate this output, 0, 0, and 0. So basically, we activate the output, all right, which corresponds to the value of the, the encoded value of A and B. So that's why this is right here. We say that this is the encoded value, and this is right here the decoded value. And that's why we call the circuit decoder. So this is a decoder circuit. Okay, so notice that here in this circuit, I have two inputs, 1, 2, A and B, and the outputs are 4 because the number of outputs is, in this case, in my circuit here, n equals 2, and 2 to the n equals 4. So 2 to the n equals 4. So I have 2 to the n equal 4 outputs. Also, observe that I activated the output by the value 1. The other output are deactivated by the value of 0. In this case, active 1, deactivated, 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 activated of a value of 1, deactivated, deactivated, deactivated. In this case, I call this decoder active high decoder. Well, as opposed to what? As opposed to active low decoder. Okay, well, how would an active low decoder behave? Well, I'm going to use the blue color for an active low decoder and show you the differences here. Active low decoder include as extra inverted outputs. And therefore, if I may extend this table here to show the outputs for active low decoder, this is here, for instance, let's say D3, D2, D1, D0, an active low decoder. So this is my active low decoder will behave as such. The output will be here. All are ones except D0 because 0, 0. In the case of 0, 1, 0, the rest are ones. The rest, in the case of 1, 0, D2 will be 0, the rest are ones. In the case of 1, 1, sorry, uh, it is a 0 here, and the rest are ones. So I want you to notice that here, that that the activation and the active high occurs by asserting a 1 on the output, and that indicates the decoding for the active high. Oops, for the active high decoder. For the active low decoder, though, it is asserting a 0 which activates the output. In the active high, an output of a 0 indicates that the output is disabled, okay, not active. And in the active low, an assertion of a 1 indicates that the output is deasserted. Okay, so this is a review in general of what decoders are. Now we can look at um, one more detail, which is let's just oops, that decoders can include an enable input. So what we said, let's go back to our example here. We said that, you know, we have input A and we have input B, and we have these four outputs of the decoder, D0, D1, D2, and D3. And then there is this enable here. Sometimes they use E or EN. Okay, so an enable line. And the job of this enable really is to disable the operation whenever E equals 0. So if we have a truth table here, okay, let's for instance um, have here the E and then A and then B, okay, and then we have the D3, D2, D1, D0, okay. Whenever the enable is 0, regardless of what's the input, all the outputs are deasserted, meaning they have value of 0. They are deactivated. Now, when the enable is 1, then I look at what's the value of A and B. So this is 1, 1. So in this case, the value of of uh, of A and B is 0, 0. So I activate D0 and deactivate the rest. Notice enable equals 1, and then AB 0, 1 with enable equal 1. So let's activate D1 and the rest are zeros. And then when I have AB equal 1, 0, okay, that's D2, the rest are deasserted. And um, when when enable is 1 and the A and 1 equals 1, 1, and then I will activate or assert D3 and the rest are zeros. Now, notice that for my students, we always say that the height of the truth table equals number of inputs. So how many inputs I have? 1, 2, 3. So that's 2 to 3. I must have 8 combinations. But really what I have here is just 1, 2, 3, 4, 5 combinations. Well, what happened to the other 3? Well, eh, notice that here we are using don't care, and we can expand this don't care to 4 cases. But we have sort of merged all these 4 cases in just one case, and that saved us 3 boxes on the table. And the reason we didn't expand, I mean, you can expand this and try all these combinations, but it is all of the those cases, you will have this output. So we did this to shrink the height of the table and save some space. Okay, so you can expand those E0, A0, B0, and you will have 0, 0, 0, 0 on the Ds. And then E0, A0, B1, and you will have zeros on the B. So the use of X's here help to shrink the table and illustrate the point. Okay, so just to summarize, we looked at decoders with active high and active low. We looked also at decoders with with no enable, as we started the discussion, and with enable line. Okay, so that's basically the function of the decoder. Let's go back to the presentation and look at other things. Okay, so and that's what we are saying here. You can These are the decoders with the enables, the active high and the active low, which we already explained. Okay, so here is another example of a decoder where we have a 3 to 8 lines. So basically, you have here a decoder where you have number of inputs x, y, z equals 3, and the number of outputs, obviously, d0 or d0 all the way to d7. Okay, and this will be 2 to the 3, which is equals to 8. And now we can again examine. Now notice that here n equals 3, and 2 to the n equals 2 to the 3 equals 8. And now these are number of inputs. These are the inputs, and these are my outputs. Okay, so how does this work? We'll look at the binary value of this x, y, z, a binary value of 0. Then we activate D0. Notice in my block diagrams, I had the D0 on the other side, doesn't matter really. And when the binary value of x, y, and z equals 0, 0, 1, that is equal to 1. So that this is equal to 0. So now I activate D1. When x, y, and z equals 0 and 0, this is equals to 2. So I activate 2. 0, 1, 1, 1 equals 3. So I activate 3. This is equal to 4, so I activate 4. This is equal to 5, so I activate 5, and the rest are zeros. And this is equal here to 6, and I activate here 6. And this is equal to 7, and I activate here the output 7. This is how this works. Okay, similar to the case of 2 by 4, and we call this is 3 by 8 decoder circuit. Oops. Okay. Now, in terms of how I would draw this circuit, and obviously, let's go back to the if we see that this how is this output here? This how many outputs I have? I have 8 outputs, and I have to draw the circuits for all of them. Well, uh, so one would say let's have a K map. But a close examination of every one of those, we see that it's one only for one time every output. We don't need a key map for that because really, for example, you can see that D0 is active when X prime, Y prime, Z prime condition occurs. And this is when it is activated. You can see 0, 0, 0. So if x is 0, then this is 0 prime, and y is 0 prime, and z 0 prime. This becomes a 1. Then it is activate this output. So it's just one condition here. And so if we go back here, we can see that this is what the D0 it is activated when you have x prime. So you can see that this line coming down all the way. I'm sorry, whoops, all the way from here. So this is a z prime, and this is y prime comes in here, and this is x prime comes in here. So this is x prime, y prime, z prime. In fact, is an interesting thing here. Isn't it this look like for me min term 0 and D1 looks like min term 1 and D2 looks like min term 2, continue, and D7 looks like min term 7. So the output of the decoder, we have made a very important conclusion here, is that the output of the decoder, those outputs are minterms whenever it is active high, and when it is active low, we get max terms. That's the other important conclusion we'll make, that when we have active low, we have max terms. So the outputs of the decoder are minterms when we have active high decoder, and they are max terms when we have active low decoder. Now, here he is, let's just continue with this. So we explained this already. Yeah, here he is talking about an active low decoder. And notice that instead of using an and, we are using an and this is to produce the active low output. Okay. Also notice that he's using here an enable. So whenever this enable is 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 uh, uh, is active, uh, uh, he would. Okay, so let's just say here is this enable, actually it is, we call it active low enable in this particular case, meaning that um, if the enable is, if e equals 0, then the function, um, then the decoder performs the function decoding. Otherwise, when e equals 1, then we disable the decoder. And you can see when enable equals 1 here, okay, we have disabled the output of the decoder. There is no 0 in the out because it's an active low. And when they decode, when the enable is 0 here, you can see that the decoder is starting functioning by activating one of the outputs as low, which means that it is asserted. Okay, so in the case of 0, 0, 0, you can see D0 is 0, 0, 0, 0, 1, D1, 1, 0, D2, and 1, 1, D3. So in this case, your textbook assumes that your enable is an active low enable. Enables can be, by the way, either active low or active high. So you can follow the footsteps of your textbook here, assuming that the enable is an active low. Okay, in this case, he is trying to um, build, as we said that one of those design questions that always comes up is build this using that. And in this case, he's trying to build a 4 to 16 decoder. Notice that here 4, 2, 2 to the 4, which is 16 decoder, using smaller blocks, which is 3 to 8 decoders. So what he has done here, you see that the inputs are X, Y, Z, and W. The X and Y are fed to the design of the upper and the lower decoder, X and Y and Z, you can see. So this is here X, Y, Z, X, Y, Now, every one of these 3 to 8 decoder are going to give me 8 outputs, 8 and 8. Then I'm going to use W here as an enable. When W equals 0, hmm, then this is 1 and this is 0. This is active, this is disabled. And I now can activate the output from D0 all the way to D7, which makes sense because notice that here the number is 0 in terms of the binary decoding, and all these numbers here are giving me combinations that are ones and zeros that corresponds from D0 to D7. But when I change DW to 1, okay, then this becomes a 0. This becomes now 1. This becomes a 0. So now I will deactivate this decoder and activate this one, and then I pull the output from these D8 to D15, which are connected to D0 all the way to D7. Now, because my W will have a value of 1 something something something, which corresponds to D8 to D15. So by using this enable, right, this enable uh, line, I was able to build larger decoder using smaller decoder. Okay, all right. Now, me just finally here conclude by giving you an example here of, let's just say, for example, this is an important example because it really um, includes ideas that sort of pull this thing together. And basically here, I am going to use decoder to produce minterms and maxterms. And in this case, I want to specifically design circuit using decoders and with extra probably OR gate or AND gate. So let's take an example. Suppose, for example, I have a function f here, and f um, equals, for instance, a plus bc. If I may expand on this function on K-map, let's just quickly do that. Okay, 0 1 0 0 0 1 1 1 1 0. Okay, so A 1 1 1 1, BC 1. So let's okay, and here are the zeros. Okay, so if we express this function in terms of max terms, it will be max term 0, which is this one, and 1, which is this one, and 2, which is this one. If we express this function, let's use another color here, green, with in terms of min terms, so it will be 4 3, sorry, it will be this one, which is 3 4 5, 6, and 7 minterms. Now I need to design the circuit using a decoder. Okay, so what do I have to do? Let's start with decoder using minterms. Decoder and using minterms. If I have these A, B coming here, A, B, C inputs, obviously I'll have an output here, 1, 2, 3, 4, 5, 6, and 7, D0, D1, D2, D3, D4, D5, D6, whoops, and I have to have one more here, D7. And you can see here that these outputs, the outputs now represents for me min terms, and I have to sum them. And the best thing to sum them is an OR gate, which give me F. So we will OR what? Minterm 3, minterm 4, minterm 5, minterm 6, and minterm 7. Now, this decoder turned out to be active high. Now we will do the same thing with, we'll use a decoder, and I think you guessed it now, using active low, which will allow me to use max terms. Okay, so let's do the same thing here. Okay, so this is A, B, C, 0, 1, 2, 3, 4, 5, 6, and 7. Don't forget these bubbles now, because they will produce the max terms. Okay, so I need max term what? 0, 1, 2. 0, max term 0, max term 1, max term 2, and then what? An AND gate to produce F. Well, someone might say, this sounds to be too good to be true. Let's try one input pattern. Sure, I'll do that. So I'll use the black color here and say, suppose, for example, I have here A equals 0 and B equals 1 and C equals 1. Similarly here, 0, 1, and 1. So according to this equation, if we substitute that, these values will be A will be A is 0 plus 1 ended with 1. That should give me an output of 1 with these values. With these values, I should get a function equal to 1. Now, with A equals 0, B equal 1, C equal 1, this corresponds to the binary value of 3. Okay, so we activate this one. This is 1, 0, 0, 0, 0, 0, 0, 0. Now, one of the inputs for an OR gate is 1. That makes F equals 1, which is what we got here. Now, let's try the max terms. Okay, so the max term says that since I have an active low here, so this will be a 1. Let's see. Active 1, 1, 1, 0, 1, 1, 1, 1. Now, this AND gate has inputs of 1s, so F will be equal to 1, which is equivalent to what we predicted right here. Okay, so this concludes an example of using decoders to produce minterms when it is active high, max terms when it is active low, and how we design a function of our choice to do this implementation. Obviously, uh, active high allows me to implement f in terms of sum of min terms, and active low allows me to implement a function product of max terms. Okay, and this concludes my lecture. Thank you for listening.